All right. Hello, everyone. Welcome back. Kane, hi.
Hello.
All right. Hopefully everybody that needs to be here is here. 3 or 3. Right. So, couple of you talked about the quiz. So, quick explanation of the quiz, and don't worry about your scores on this quiz. The point of this was to pay attention to the verbatim of and understanding the meaning of fixed frame, body frame, rotating frame, all of that. So for the first one, it was a close call. Of most of the class got it wrong with the small percentage of getting it right. So this is probably how the way it was worded, and it's chosen from your book. So it is important to understand and read well and pay attention to detail. But the body frame, whenever you're calculating the velocity of the body frame, is with respect to the frame that is fixed on the body and moves with the body. So there is no relative motion between the body frame and the rigid body itself, right? So that's why when we put a frame on a joint and say this is rotating about z-axis, there are other joints in this robot as well, right? When they rotate, nothing changes up for this joint because we are going to fix this frame on this joint. Wherever it is always the same direction. So we can say that, sorry, not left hand, right hand, that the rotation always happens about the z-axis. Doesn't matter which orientation your joint has. It always moves about because those are fixed. So that question was, so probably this part, then pay attention that it moves the moving body. This one is the moving frame that is attached to the moving body. The frame is not moving. And it's definitely not a fixed frame. This was probably like answer something for the point. And the station frame that's fixed, so it's not fixed anywhere. So body frame is on the body. And then the second one. So this is in the lecture, and I paused on that one. So find that lecture, find the page. The idea again is the angular velocity omega s, which is with respect to the fixed frame, and the velocity of the body frame. They're both angular. They are the same thing, but seen from two different frames. So they are similar, right? Any question on these two clear? Again, some of these are just to grab your attention and say, hey, pay attention to this. In the big scheme of the whole class, it would not change your grade as much. So don't worry about that. And then, so this week, I'm gonna go over very quickly and then start. I posted the homework solution. Your homework will be graded over the weekend, so hopefully you will see the grades on Monday, but the solution is detailed enough that you should know what would you get. If you didn't understand any part of the homework, email me, meet me in office hours, or ask for office hours. I will meet you on Zoom separately that it works for your schedule. Should also work for my schedule. So we already went through this, yes. So today we are talking about this, and then again tomorrow, Friday, we have a guest. And participation or attending class as usual is highly encouraged. I cannot record the lecture they require, they ask, because the industry, they're going to share the information. It'll still be on Zoom. If some of you again can't be in the class, you can attend over Zoom. Those that they cannot come in the class, not you. I would suggest to be here. That's the one chance you can actually ask question about everything industry. All right. So it might even be more useful than my lectures, to be honest with you. I'm going to learn a lot myself. Then there will be no class participation today because I'm respecting everybody that is at career fair right now. But whatever is today's lecture, it would be a class participation that will be due on Monday, right? So you have time from today all the way to Monday, beginning of the class, to do this. And this would be about today's lecture, all right? So bringing everything together for Forward Kinematics. And you're also working on your homework too. Link actually is working. I don't know, every time I have to bring it there, it works. But you can see the questions. There are 2 questions, 2 and 3 that you will know today. Oh, okay, now we can solve it. All right. Now let's get back to my lecture slides. Oh, I don't know. How many of you looked at the lecture slide from Monday? Because I asked you to do so when you come into class, be prepared. Thank you, Adam. And thanks for everybody else that being honest that they didn't look at it. So what I did was, I'm going to show you, but I'm not going to go over because I want you to do it yourself. So because there was a lot of question at the end about like what happened to that example I solved, right? To this example, I added 3 different cases of how to write a screw axis. We're going to go over all of this in Forward Kinematic as well, but this is where you should learn it. And then Forward Kinematic is to use it. All right. So when you're reviewing this lecture and today's lecture to do your class participation for Monday, this example will help you. All right. So I'm glad that I remembered to show you, because otherwise you would say I'm a bad teacher. All right. So we stopped at the screw motion interpretation. I kind of talked about it. When we have a screw motion, we have a rotation and a translation, right? Now imagine that this screw motion is happening and is off-centered from the fixed reference frame. You remember there could be a Q between the origin of the reference frame and the origin of the axis of rotation. So we are going to have different velocities generated here. One is the velocity generated because of the angular motion. One is the translational velocity along the pitch of your screw. And if this screw if this axis is off-center to the fixed frame, there will also be an element of omega cross product of Q, right? So this would be a negative omega cross product of Q. And if you remember, last time I showed you, there was, let's say this would happen. And so this is your omega. And we are measuring it right at here because we are putting a fixed frame there. We are measuring everything with respect to one point. Now, this generates a velocity in the negative direction of, well, if it's the y-axis, you have to see which axis it is. It's not always y-axis, but it would be in a negative direction in one of your axes. So this would be V. This V is the negative omega theta dot, which is your omega, your angular velocity cross product of your Q, which will be simplified as distance times the angular velocity, right? So we have that, that's fine. So is it like centrifugal first or the other one? I need to check that.
It was in the other way, like switch the theta or the opposite direction.
Then you find it in the other direction.
Okay.
Yes.
But it's still, in this case, but it's still.
So you will have the good question. You will have the positive direction of this joint rotation.
Okay.
So if this moves this way, it's still measured at this point up.
Okay.
Right? So all you have to do, find the positive direction of rotation. If it is going through the origin of your fixed frame, then you don't have it. It's always for the joint that is offset, right? So let's say my fixed frame is here. So these 3 joints, you don't have any offset velocity generated by that. But for this one, it will be, right? If this was robot and was going to move, if I wanted to find, then there would be. Now I have to find what is the positive direction here, and then try to find the velocity in this one, right? All right, so this is just to give you an idea like how the screw motion works, and then we kind of talked about a screw axis. So don't mix them up. Now, we have a new vocabulary again, twist, and it's defined as, so your screw axis is a normalized twist. We've already seen this before, right? So you have a point on a rigid body and there's screw motion happening with the speed of theta dot. When I say screw motion, there is rotation, there is a velocity along the pitch and is off center, right? So your P dot or your velocity will be a combination of those three. There are three elements that are contributing to this. The angular velocity part is only omega theta dot about the axis of rotation. But you have two components of the linear velocity. One, because of the pitch or the linear motion. The other one is because it's off center. So there will be that velocity as well. We can put this as a twist defined as an omega s and bs. So when I say s, what does it mean, that subscript s, based on what we have seen before? With respect to a fixed frame, right? So you always have a fixed frame, you're measuring everything from it. So different joint could be under screw motion. When you're writing their twist, you're always measuring with respect to a fixed frame. So everything is with respect to fixed frame, but they're all related and they're following the same directions. Now we can put this in a matrix form, and you see that here theta dot is you can take theta dot out. So there's a matrix theta dot. So Vs would be this matrix times theta dot. For this vector. So that would be your twist, your twist. So again, just to remind you, this is induced by angular velocity. And this is your linear motion. Now, you might say, okay, so let's think about what if one of our joints was not a rotary joint, it was a prismatic joint, right? This should still hold. What will happen? What would be your omega s if it was a prismatic joint? 0, right? Because there's no rotation. In the linear velocity component, which component would be 0? The first one, because it has omega in it. So when you don't have rotation, you don't have linear motion induced by rotation. There's no rotation, right? So the other component is the linear motion. Then you say, okay, there will be linear motion, but it's not following h omega theta dot. What would it be? The velocity of your prismatic, right? V. If you remember, we had it a couple like last week. So this is the general form. It still has to hold. So we are being smart what will go in there. All right. All right. We need to have coffee. All right. I'll let you have this one. On Friday, I coach CrossFit at 5 a.m. Then at 6 a.m. and 8:30. Go teach a class at 11. Have office hours and come and go work at that class. I think I said that it's Friday, like I'm out of back, that's why I was a regular day. But today I slept like a baby. Well, like until 7, but yeah. All right. Now bring it all together. Now let's say that you have a rigid body that has linear motion and then rotational motion. You're going to put all together. We learn about screw axes before we learn about transformation, right? Homogeneous transformation. They should all match because again, there's our different interpretation or representation of the same motion. How do we relate that? We can write, we already know that. So T(S) of B is transformation of B with respect to S, or S in S, which is the rotation between them and the translation between the versions, right? Could be 0, could have a value. Now, we can say the body twist and the fixed twist or the special twist, they are related to the transformation as such. So the body twist is T inverse of S B multiplied by T dot. You already know how to do this. Remember, it is element one. To find the matrix, then you just get the differentiation of each derivation of each element. Now, if we have Vx with respect to a fixed frame, we just put them. It makes sense because we're looking from the body frame. Now we are looking from this. So it has to be just the inverse, like the direction is being put. Now, twist, body twist can be written as, what is this? This is angular axis. What is this? Okay. What is it? What does this tell us?
Okay, so there'd be angular velocity.
Yes, that's the angular velocity axis. But what does this bracket mean?
Oh, right here.
New symmetric representation of that. So this is 3 by 3, 0, 3 by 1, 0, 5, 4 by 4. Because this is 4 by 4. It has to match, right? So if you have the omega v, the axis of rotation, and if you have vd, the velocity, if you put them in this form, you can drive your transformation from it. It's going to be your body twist. All right. Now, if you are following your book uses body twist and picks the spatial twist a lot. So become familiar with those terms, but in simple way, it means that what's your angular velocity directions, what's your linear velocity direction, and then put them together and represent the system. So these are, this bracket is matrix representation. This one is a skew symmetric. Representation. Just don't get them confused. So VB twist itself is omega B, and well, so linear and angular velocity transpose. This is body twist. VS transpose spatial or fixed frame twist. I posted 2 videos in this page, which is the authors explaining forward kinematics to you, and they will use body twist a lot. So I just want you to know what it is. All right. I use school axis myself because that's what it is. So. Now the beautiful and sweet topic of forward kinematic. I have been waiting for it since day one. All right. So this is a little bit of fun before we get back into unfun topics. Well, that is just difficult. So unfun is boring math stuff that you have to actually do. All right, so from your previous knowledge, from things that I talked about, what do you think is forward kinematic when we say forward? Spoiler alert, there's an inverse. All right, so what is forward kinematic? Yes.
You know where linkages are, everybody know where.
Very good. Okay. You have a water class or something before? No, great. So, what does that mean? I'm going to use our unactuated robot. If this had motors, it would be automation, right? Doesn't have motors. So, this is unactuated. This is just like a free ball and bearing. This is our base. This is rotation.
Yeah.
This is rotation. Well, I'm gonna miss this. Of course, okay, it's fine. It's just a light. Nothing's gonna happen. Hopefully, yes. There is one here, and there is one here. R, right? Now, when we go from, we know how much each of these are rotated. All right, so we have the angle of all of this. We want to find out where this end effector will be placed. That's forward kinematic. So we define the position of and orientation of our end effector, knowing every joint's value. So what do you think our approach should be in this scenario? What we have done so far, why we came to class for groups to do what? I mean, other than meeting. What we have done so far?
Your position.
We talked about position, we talked about orientation, right? Talked about velocity. If you remember, I said we need to model our system, right? So all what happened so far is all the tools that will help you to model your system. When we say model of our system, what does it mean? Okay, so we are gonna go from an actual system to a mathematical expression to a computer program, right? So you can show what happens, the model. Now we have to do this jump, like we go from, so we understood everything about the robot. If you look at the robot, you're like, how many joints does it have? What direction is rotating? Where is the reference frame? So you can all ask those questions right now and you can answer them. Now you have to represent the mathematical equations for this system, right? Forward kinematic, we're going to do that. We're going to drive this mathematical representation equations. Then we plug in the values for theta in this, and it will give us a position and orientation for the entrance. We keep changing those, this will change. So you start theta from 0 to 45. For all of those, you can see how it's moving, for example, right? Now, in forward kinematics, since we only care about the joints and how far they are placed from each other, which is the length, and we are not assuming any mass and any forces. We didn't talk about forces. We're just trying to figure out the configuration, right? Where would be the position. So no force, no mass involved in kinematics. We will involve them when we talk about dynamics, which is after inverse kinematics. Now there are two different, there's one simple way of writing forward kinematic equations. Let's say that if you have this robot, so it's 1, 2, 3 arms, robot has links. If I ask you what's the position of this last thing, one simple way is, okay, find out what's the x, what's the y, right? So get an equation for x and y. And then you also know that you have three angles, theta 1, theta 2, theta 3 involved there. So by putting those values, you can solve this. So you basically need three equations and three factors, right? So you can write this simply and solve. That's one way of solving it. But now if it is more complicated, if these joints are not rotating in the same direction, because all these joints are rotating about z, all these are in the same direction, they're parallel, right? That's the simplest case. If you add 10 more rotation, it's easy. You just have more emphasis. Sine, cosine, and principle. Now, what if one of them becomes in a different direction, becomes 3, or now we're thinking about x-axis? You could still do this graphically. It's harder to match, especially if it's more complicated. They have some like 2 or 3 joints on top of each other. They're not in the same direction, rotating like the ball and socket. Then we need a different method. Now there are 2 different methods out there that you could use for forward kinematic. Approach 1, product of exponential or PoE method, which we have built so far toward that, and that's what is inside your books forward kinematic, and I told you before. The other one is we are going to assign different sequence frame, pitch join, define some links, some distances, and use and create a table, which is called after their inventor Devin and Huttenberg's DH table convention. So you do frame assignment and then you create a table, you multiply things in the table and it's all. This method has a lot more upfront work. The solution is simple once you have the table. That other method is easy to create the model. It's just a lot more processing after you have your model. So for some systems, if you remember, if you use one method versus the other, you choose which one. Just be careful. When I give you an assignment to do, especially if it's in this, I'm using a new standard. Most of the examples out there on the internet are the old standard, so I don't know. All right. And the reason I'm using the new standard is the new literature using that. So for now, we're going to focus on production of exponential. Imagine a robot. You're going to start with a simple all rotation about the same axis. So the same robot you saw from top view, now you're seeing the screen motion of that. This is where you want to pay attention. So if you are on other devices, if you're taking a nap, you want to wake up for this one. But this is the fundamental, everything else should be straightforward. This is your base. We put our fixed frame here, right? Now, you see this, right? Go all the way, that has an M next to it. That's our end effector. We want to define the position of our end effector, right? So that first configuration is home position. So the robot is currently being everything at 0. Now, home position means all theta and all, if you have prismatic, all of them are at their 0 position. Whatever configuration it looks like, that's the home position. It could be straight up, could be straight down, it could be angled. So you will put all theta equal to 0 to find your home position. Now, we want to know what is the exponential coordinate of each joint with respect to our base. So we basically move along the joints, write their exponential coordinate, go to the next one, go to the next one. Now, do you remember the screw axes? So you write a screw axis for every joint, which is this F. This is your big matrix F, e to the power of S, theta. We call this exponential coordinate, right? So the exponential coordinate. So basically finding this for every joint. Now, moving from one, when we find this one, we are assuming that the robot has one joint. What is the exponential coordinate? Now the robot has 2. Now the robot has 3. Now 4 joints. We put all of them together, we multiply, and it will give us the model. You're walking from joint 1, walk all the way to end effector. So you're walking through all the joints. Now there are 2 ways of doing this. One is with respect to the base frame, which I will teach that. You could also write everything with respect to the end effector frame. There's no difference. It's just your reference frame is at the end. So everything is with respect to the end frame. Right? If you're reading your book, there is a second formula. I'm not teaching that one because it's not very practical. Usually you want to know where your end frame is with respect to the base frame, because your base is usually on top of something else, right in the center of something. There are a couple of key concepts here, and you saw a few things on the slide. One is, what is this M thing that we saw there? Well, here, what's this M? You remember that this was your home position. So M is your home position. M is a matrix that represents the home position of your end effector. Now, all of these are homogeneous transformations. So M is 4 by 4. What do you think is inside M?
would be the position and the rotation of it.
Yeah, with respect to the base frame, right? So, because we said we want to know what's the home position. If nothing moves, where this M is. So there is a frame on that, there's a base frame, and you want to know what's the position in XYZ direction and what's the orientation with respect to that. That becomes what goes inside your M. 4x4 matrix and shows the orientation and position of your end effector at home position with respect to your base. To do that, you need to identify your base frame to the direction of X, Y, and Z. And then you have to identify, put a frame on your end effector and then identify the direction of X, Y, Z of that. Can we have any direction? Yes. Should we have any direction? No. You want to make it simple. The more zeros are in matrices, the easier is the calculation, right? So we're going to choose ways, directions that gives us a lot of zeros in there. So there aren't many numbers in there. Then we have to apply our screw motion to each joint to find those bracket S1, bracket S2. So first we find S1, S2, S3. We put them in the bracket format. And then once we have that, we would put them in this form. So this is your home position. This is joint 1, joint 2, joint 3, all the way to joint 10. Now, what does this mean? TSP theta 1 already.
That's the transform of the body with respect to the fixed axis based on a function of theta 1.
Meaning that once you have this will have variables of theta 1 to theta n. Now, if you give them numbers, you can plug in there and it gives you a, so the solution would be the 4x4 matrix that has numbers in it, right? For a specific angles, it will tell you your orientation and position of the end effector. Does this make sense at all, what I taught? If it doesn't, raise your hand now so I can repeat it. Okay, I didn't see a hand. That's good news. We're gonna go over all of them again, don't worry about it. So. Through an example. So I'm gonna use an example and go over this. Hopefully it should help you. You see that in this example, I gave you all the directions, all the axes are defined and assigned, right? For the time being, I'll do that for you. Once you learn how things look like, you can assign them yourself. Now, write in matrix for me. So first of all, identify where is the end effector. Use frame 0, 1, 2, 3. So usually you want to find your last joint. End effector would be for now coinciding connected to it. So it's frame 3, right? If you said I'm going to put it here, fine. There will be a distance that you can include, but it doesn't matter. It doesn't change anything in the orientation, and the position is a fixed number. So we can put it here for now. All right. Now write M matrix. What is M? So you write your home position matrix. You're writing everything in base frame, right? With respect to base frame. I'm gonna help you a little bit, then I'm gonna fill in the blanks. There's going to be an army, a rotation here. There's going to be P, and there is going to be 0, 0, 0, and 1. So if you, I'm gonna do this. Just take these ones out so I can fill in there. So if you are comfortable so far, have been comfortable with finding the rotation matrix between two frames that you have practiced so far, right? And the position of the origin between two frames representing another frame, you should be able to calculate this very quickly. Yes.
So, it's like blind. Frame 0 at frame 1, that means like frame 0 is.
Yes. So if you see that line or that line, means that they're on top of each other. The origins are coinciding. The directions might be different. So this just means that these two coincide. Now, so we're trying to find Z3 direction in Z3 frame in frame 0. So we have 0, this is X3, 0, 0, 1, negative 1, sorry, 0, 1, 0, 1, 0, 0. Then the P position, the position of the origin in this frame, so you have L1 here, L2 here, it's going to be L1, 0, negative L2. If this took you in a while and you didn't know what to do, please go back and review past frustration and your assignments. This is the simplest part of everything from now. All right. Now, the next thing is that we need to identify how many joints do we have. Why? Because we need to write the screw axis of each joint. So we need to identify our joints. How many joints do we have? 3 joints. So you can see from theta 1, theta 2, theta 3. So I have 3 joints. You have the direction of their rotation, correct? So 3 joints gives us 3 screw motion. I need to find S1, which is omega 1 V1 transpose, right? This is a screw axis. So in your homework and in your exam, I will ask you to give me home position and screw axis. If I ask that, you have to provide exactly what I asked. You can't solve all of it to the end, because that shows you didn't understand what's what. You just memorized everything. So it is really important that you understand the terminology. I'm spending a lot of time, and I expect that we are all on the same page. Now for S1, so let's say I need S2 also and S3. So these are 3 screw axes I need, omega 2 V2 and omega 3 V3. Now a cool tool here would be a useful tool, let's say, to create a table and then say joint I, omega I, QI, and VI. I'll explain what QI is. So we're doing this because after modeling, we're going to program, right? So I'm kind of setting it up in a way that I would probably program it, write the code, but basically organizing the information. So I know I have 3 joints, 1, 2, 3. We know from before that our omega i's are our, so the omega I velocity is our omega I axis, the axis of rotation, and our linear velocity is a combination of 2 things, omega I cross product of QI plus VI. if we had a linear motion separately. So you would not have both of these at the same time, correct? Why? One is induced by rotation, one is the prismatic motion. But you're writing the general equation, right? Now it's easy. We are going to write our screw axes, and then we can write. So for this example, we're just going to write the screw axes and then find the end position. All right. So we are not doing this one yet. We are just finding these values plus this guy. Now, let's see what is our omega 1 is. So for first joint, what is your omega 1? It's measured in your base frame. Basically, find the rotation axis and tell me the direction of that in your base frame, in your fixed frame, frame 0. I heard something correct. Someone said it. I think you said 0, 0, 1, because this is the axis of rotation and is in the same direction. It doesn't have any component anybody else. 0, 0, 1. What is your QI? What's the distance between the origin of frame 1 and origin of frame 0? 0. Do you have any induced velocity? Omega cross product of 0 is 0. It's not offset, so there is no velocity being induced here. So my commas and my ones, they look the same. I don't know what to do. I'll do my best to write my zeros larger so you know what's going on. So S1 is 0, 0, 1, 0, 0, 0. Do you remember it should be 6 by 1? So I created S1. Now you write S2. Go through the same thing. So S2, you're writing it for second joint. If you can write that. Just to remind you that it is important you just tell me where I pass. I'll let you review this when you're studying. Go through all of that. But it should be straightforward. If you understood this one, it should be straightforward. So the direction of that Z2 is in the negative Y direction of your frame 0, and it doesn't have any component in the other direction. You'll find your QI, which is the center of or the origin of the second frame with respect to that fixed frame. L1 in the direction of X1, and then for this, we use that. Some of you might be able to find out where the direction of the velocity is, but you don't have to. You can bring this to your exam and do it. You could do that if you're sure that you're right, but I'll just follow this. You'll find your VIs and place them here. Now, this is a straightforward case because you only have rotational, right? You don't have any prismatic so far. So you just have to find omega, and you will have induced for all of the off-center joints and 0 linear velocity for the one that goes through the joint. Through frame 0, sorry. Now, if I asked you, find an expression for forward kinematic, then you have to say theta, so sorry, T is e to the power of S1 theta 1, S2 theta 2, S3 theta 3, M. You have M, you found all of your axis. Now you have to create matrix representation of your S1. And if you remember, the equation for SI matrix representation was skew symmetric I, VI, omega I, VI, 0 and 0. So basically putting omega 1 skew symmetric, right? V1, 0, 0. You create this, you show this for all 3 of them. And you have M, so that would be your T. Now, for now, we leave it here because you can't solve e to the power of a matrix right now by hand, right? There is a formula that you can use and convert this to matrix representation, and everything becomes a matrix, so you can use your calculator. Right? If you're coding, you'll probably be able to use that, but we're going to get to the matrix level. So there are 2 kinds of questions. Your homework has both kinds. So pay attention which one is which. I will give you a 0 if you just solve everything, because you understand what happened. Sounds good? Now, so you're done. I put another example here. This one. So we don't have time, but I will put the solution there for your study. So study that as well. And then this is your past participation. It's kind of in the same direction, like it's not complicated. You should just be able to go through it. All right, see you on Friday.